the top of the hour, so it's time to kick off this new best session for this virtual IETF 112. Not well? So if some people are not aware about it, please read it, but it should be well known for most of the people. Here is our agenda. It's pretty packed. So to all the speakers, please keep your timing and don't overlap. Otherwise, we will have some issues. We have a very limited buffer today. Status update. So we have 4 RFCs that have been published since the last summer IETF. 2 are really interesting. So it took a lot of time, but at the end, we succeeded to publish the 2 RFCs that are related to EVPN routing, so the IRB EVPN as well as the IP prefix advertisement. So this is it took a lot of time, but this is a very good achievement. We have one RFC in the RFC editor queue, which is the proxy ARP ND, and we have bunches of RFC drafts that are either under Martin's review or at the IESG stage. We have 2 documents that are still under Shepard's review, one which is related to EVPN LSP ping. So Matthew, if I'm not mistaken, has to do the write-up on this one. We have also the unequal load balancing. So I think the review has been done. So this document is just waiting for some dependencies to be solved before we move forward. Otherwise, I think we were good on this one. We have one document in our working group last call queue, which is the EVPN fast DF recovery. We have 2 documents that are still under working group last call for a long time. So on the ICID CMAC flush, unfortunately, we got very few feedback and responses during the working group last call. So Matthew requested a routing directorate review on this one. So I think Russ was appointed and provided a couple of comments that the authors have to answer before we can move forward. On the EVPN WS, VPWS FXC, I think on this one we got a good amount of support to move forward. However, we are still missing an IPR reply from Ali. So as soon as we get it, I think we will be able to move to the next step. Similarly, we have the BGP, eBGP, DMZ draft under working group adoption, but we are still missing some IPR response. So I don't know if we have Satya connected. No, Satya isn't there. So yeah, to the authors, please reply to the IPR poll so we can move forward with the adoption. Working group document updates, so you will be able to review offline. So this is the latest update that we have for the documents. Couple of things to highlight. So on MHPA, so multi-domain protective, there was a working group last call that failed. It seems that the comments have been addressed by the authors, so I need to check if everything has been resolved, and then we can move forward. EVP Geneva, there was also a couple of comments received during the working group last call that needs to be addressed. EVP and IPVPN interworking. Oh, Matthew is telling me that my audio is breaking up. Do you have some issue to hear me properly, Matthew?
Yeah, your audio is clipping. I don't know if anybody else has that problem or if it's just me.
The same problem, but I can hear Matthew fine.
Okay. So Matthew, do you have the ability to share the slides on because it may come from...
Yeah, I don't have them downloaded. Keep trying. It's usable. It's just clipping for a bit on this one. Let's see if we can get through this, and then we'll be on to the other presentations anyway.
Okay. So on EVPN, IPVPN interworking, so we had a chat with the IDR chairs a couple of weeks back. There are some pending questions.
All right, I spoke too soon. You cut out completely now. Okay, thanks, Stefan. I'll talk over these now. So for the multicast flow DF election draft, we think this is going to be ready for working group last call soon. So that's in our queue. The MVPN seamless interrupt draft is on the agenda today. EVPN BFD and SD-WAN usage. So EVPN BFD, do any of the authors in the meeting that they can give us a quick update on that? Okay, so I treat that as ongoing, I think. SD-WAN usage. So Linda has asked for working group last call on that. We've just got an open point about whether there's a dependency on that and some companion work in the IDR working group. I don't know if Linda is in the meeting to say something. Yeah. Go ahead, Linda.
You're asking me to do some. Oh, the companion work in IDR has been adopted in IDR. And so this is the base document that one depends on, because this is the usage basically showing how BGP used. Over there has some BGP extensions. So I hope this one finish first before that one can finish.
Okay. But there's no normative dependency of this draft on that one, right?
No.
Okay. So go ahead.
Excuse me. The drafts are independent. The one in IDR can go toward working group last call, but remember IDR requires 2 implementations. Thank you.
Thank you. Okay. So I think apart from that, we'd like to see a little bit more working group review of this draft. So we'll probably initiate, well, we will initiate and request a routing area directorate review of the draft. And please do review the draft and send any comments to the list. The multi-homing split horizon draft. So we believe that's ready to progress to the next step, which would be working group last call. The extended EVPN optimized IR draft. So the authors have said that they believe it's ready to move forward. Martin's waiting for the the bump procedures draft to move ahead for this one. BGP multicast, this will be ready for working group last call after an update of the document. The IRB extended mobility draft is ready to move forward. Now the dependencies have been resolved. And as we stated before, the Yang models are mostly on hold for the time being, while we progress some of the other work. Next slide. Okay, so the RFC 7432 BIS draft. So there were a few changes in this. I don't know if any of the authors are in the meeting apart from Stefan, who can maybe talk about this update.
Luke, do you want to the update? Yeah.
Yes, go ahead. Thank you.
Sorry. Yeah, so it's actually 02 is actually a fairly mechanical update. So we received 4 sets of feedbacks. One of them actually is a bit of a slip or a purposeful omission from RFC 8584, I think it is, or 8534. The DF election draft previously sort of specified how to auto-extract ESI import route targets, but that was removed at the last minute before publication. So that's incorporated here. And then the other, I guess, substantive changes in section 8.5. It's specifying the DF election behavior for 2 different originating IPs. So in AFI v4 and AFI v5. And the rest is fairly mechanical. Wording changes and just updating sort of the applicability of flow label, both signaling and in data.
Okay, next slide.
I think we are done, Matthew. We can
Okay, so thank you. Next up is Kesavan. Stefan, if you could share the slides for the MVPN seamless interop draft. Do you want to see if you can take over now, Stefan, see if your audio is improved?
Yeah. Okay.
Thanks.
Hello, everyone. Can you hear me? Hello?
Yep. Yep.
Okay.
Good. Thank you.
Hey, everyone. This is Kesavan Sami from Cisco. This is about an update to the existing EVPN seamless interop draft. So this draft describes a procedure to do seamless interop between EVPN and MEPN PE. The same procedure can also be used to do optimized inter-subnet forwarding within EVPN fabric. Oh, this is an old slide deck. This is an old slide deck. So can I share the new one?
Yeah, go ahead. If you request it, we can give you permission. But I'm trying to grant it, and this is not doing it. There we go.
Uploaded the new slides for case 1 and Jeffrey's draft.
Can you see my screen or no?
Yeah. Well,
okay.
Lots of recursion on the screen. That's good. I can see PowerPoint now.
Okay. So, so this draft has been adopted as working group document in 2019. So interop with L2 EVPN PE was not covered that time. So this has been covered now. In addition, few sections has been reorganized. So I'm primarily covering L2 EVPN interop part right now. So what's needed for interop? So a gateway device needed to do interop with L2 EVPN PEs. A tunnel domain can be provisioned with one or more gateway device known as seamless interop EVPN gateway. So PE, which is configured as gateway, must be provisioned with all BDs that are available in the tenant system. So given set of eligible PEs, one PE is selected as a DF. So any of existing EVP and DF election procedure can be used for this. So there are 4 possible use cases depending upon whether the remote PE or local PE supports IGMP MLD proxy. So this can be supported either at seamless intra PE or remote PE, or few set of L2 EVP and PEs. There are 4 cases, but primarily we will just build L2 multicast state either by SNAT out or IGMP control plane, depending upon whether the remote PE or local PE supports MLD proxy draft. So operation overview. So given set of eligible gateway nodes, one node will be elected as a DF. So the DF will detect a remote PE capability, and based on that, it tries to learn L2 multicast state either through SNAT route or IGMP or PIM control packets. So the DF will act as a LHR for receiver behind L2 EVP and PE with respect to other seamless intra capable PE as well as MEP and PE. The DF will also act as a FHR for sources behind L2 EVP and PE with respect to other seamless intra capable PE as well as MEP and PE. So the DF uses BUM tunnel for traffic forwarding towards L2 EVP and PE. The DF uses WERF tunnel or MEP and tunnel for traffic forwarding towards other MEP and PE as well as other seamless intra capable PEs. So this is quick overview. So assume that so here the blue nodes are seamless intra capable PE, and PE4 and PE5 are seamless intra capable PE, which are configured as a gateway. So between these 2 nodes, assume that PE5 got elected as a DF. Now it tries to send SNAT start out to pull all source traffic towards DF so that it can act as a first hop router. So assume that now sources are attached behind PE8. So as soon as source starts sending traffic, so it's going to send traffic towards PE5. So PE5 will start advertising IP VPN and EVPN host routes towards EVPN fabric as well as MEPN fabrics with associated web route import community. Now, assume that we have a receiver behind PE1. So when it detects MEPN SAD routes, it starts sending MEPN type 6.7 towards remote PE, and it starts pulling the traffic via WERF tunnel. So now this is for L3 case. Now assume that you have a receiver behind PE7, which is L2 EVP and PE. So this can send the interest to DF either through SMAT route or IGMP control packet, depending upon whether PE7 support IGMP proxy draft. So now assume that we are just learning L2 multicast state at PE5. So once we learn the state, then it's tried to create L2 state. Then again, it sends a request to IRB interface. Then we will just create L3 state. So now when PE8 sends a traffic towards PE5, so it does like a local routing on IRB 30. Assume that a receiver is behind VLAN 30 at PE7. Then after routing, it will try to send the traffic towards the PE7 using L2 state. Now, so this is about source behind seamless intra PE. What will happen in this case? It's pretty much PE3 sends PE5 will pull the traffic from PE3 using MEPN signaling when it has a receiver behind PE7. So PE5 doesn't advertise any host out. PE3 will take care of that. This is about new flags in EVP and multicast extended community. So this multicast flag extended community is defined in IGMP MLD proxy draft. So bit 14 and bit 15 are used by IGMP MLD proxy draft. So now we have proposed 2 additional bits for seamless interrupt draft. So bit 13 indicates seamless interrupt capable PE. and bit 12 indicates that this PE is capable of acting as a gateway. So so all eligible gateways will set these flags, and one of them will allocate as a DF.
Okay, Kesavan, can you try and wrap it up, please? Because I think we're out of time on this one.
Yeah. So this is last
Thank
slide.
Okay.
So yeah, so this draft has been around for almost 5 years. Yeah, it's widely deployed. Requesting last call. If there are any comments or feedbacks, we will just take it.
Right.
Jorge, really quick.
Yeah, hi. Can you hear me?
Yeah.
Yeah, very quick. So the bits 12 and 13 in the multicast extended community are taken, and they are actually used in 2 drafts. One of them is in last call, the OISM draft. So yeah, we should remove it from this draft as soon as possible. And the other comment I have is the OISM draft also defines procedures for L2 multicast interoperability. So I wonder if you look at that draft for that specific procedure.
Yeah, so I looked at that. So both are handling 2 different problems. So yeah. So why isn't it purely based on EVPN signaling, etc.? It's here like we are just using EVPN signaling between EVP and PE. So some additional procedures are required. So that has been captured here. So with respect to bits, yeah. So when I looked at last time, so I haven't find any bits. So that's why I just took it. Yeah, I can just take a look at that. Then I can just move the bits.
Yes, please.
Sure, thank you.
Okay. When unfortunately we don't have time, we have to move to the next slot. So if you have a question, please take it to the list. Sorry.
Sure. Thank you.
Okay, next presenter, Luc-André.
Hi. Should I share my screen, Stefan? Or?
I'm sharing. Okay.
Okay, perfect. So I'll be presenting draft BuildFS EVPN fast reroute on behalf of my co-authors Patrice and Takuya from KDDI. So this draft takes a look at EVPN convergence solutions that exist today and how convergence is achieved for EVPN deployments. So EVPN-based convergence is largely control plane driven today. It's route scale dependent, topology dependent, and largely depends on any delays in the network, right? Route reflector, network delays, and so on. So there is a straightforward solution, which is using the peers service label as an edge redirect. However, there are 2 major problems with this solution that sort of has been floating out there for a while. The 2 problems are basically that if we use this peers service label, it may lead to loops in the network between the 2 peering PEs, or extra data plane work to prevent that. And using the peers service label for redirects actually does not work for all existing load balancing modes. So with that premise, effectively EVPN convergence can't reasonably meet any sub-second or even more stringent than sub-second convergence requirements. So on the next slide, this draft proposes an approach to achieve fast convergence. So the only way to achieve rapid convergence for EVPN is to remove the reliance on the control plane. So what this means is effectively local failure detection at PE1 and local failure restoration at PE1, where then the control plane, so then the EVPN procedures would kick in as we know them, right? The EVPN mass withdraw and the correction of the control plane. So this draft addresses rerouting EVPN traffic at the edge. In particular, I'm going to go over issues with using the peer service label. So the issue of the continuous reroutes if multiple failures at PE1 and PE2 are detected. And in a second step, I'm going to be covering effectively rerouting to a non-DF interface. So in the next slide. Okay, so in EVPN all active, if you consider two PEs that are connected to a CE in all active mode, which is a fairly typical EVPN deployment, and you have a failure that occurs at the south switch. So what's going to happen is the lag failures will be detected simultaneously at PE1 and PE2. So with any kind of reroute active, it's very easy to observe how basically PE1 will be redirecting to PE2 and PE2 will be redirecting to PE1. and that's going to continue until it's going to generate a traffic storm between PE1 and PE2, and it will continue until either TTL drop or forever. So if you go to the next slide, the solution proposed actually it proposes a specially allocated downstream label, which I call the reroute label. And what's different between this reroute label and the standard EVPN service label disposition is in standard disposition, basically, the traffic from the north, from PE3 to PE1, will use what I call a state-based forwarding chain, depending on the AC. So if the AC is up, the traffic will get sent from PE1 to the switch on the south. If the AC is down, typically traffic will be dropped. But if I use, for example, the peers reroute label, the AC down can be re-encapsulated with this reroute label. So far, so good, and that's basically the same thing as the proposal using the service label. However, by using a specially allocated label at PE2, the disposition of the reroute label at PE2 of the once rerouted packet is terminal. So it's a final disposition, right? So this disposition occurs at PE2 of the packet that was rerouted from PE1. And it happens regardless of the AC state. The packet is either forwarded or dropped into the AC. So in this case here, where both ACs are down, the packet coming from PE3 that arrives at PE1 that is effectively rerouted over to PE2 arrives at PE2 with the disposition label that doesn't care about the AC state. So if the AC is down, PE2 will not try to redirect this packet. So the once rerouted packet that comes in with this special label will now get dropped. And so because this is a downstream allocated label at PE2, there are no data plane modifications required. I don't need to change anything in the core. I basically need to track only a special attribute on that label at PE2 and advertise it into EVPN. There's also no extra labels on the stack, so I'm not adding a label onto the onto the forwarding stack. It just replaces the service label for the traffic from PE1 to PE2. On the next slide, so this is a bit of a heavier slide, but the premise is actually very simple. If the switch, or actually, sorry, if PE1 and PE2 are operating in single active mode, what you'll see is effectively PE3 sends traffic to PE1, which is down. So without a reroute, we lose traffic at PE1. If I use this reroute label, or if I use, for example, the service label, PE1 reroutes to PE2, but I haven't really gained much there because PE2 is still waiting for control plane to converge. So PE2 is still non-DF and will drop the rerouted traffic. So by allocating this special reroute label, again, it's the same label as the previous use case. This reroute label carries effectively a context of the fact that it is a once forwarded packet. It is a reroute packet, And at PE2, it has a special characteristic allowing it to bypass DF election. So while control plane is busy reconverging over to PE2, this once rerouted packet will actually bypass DF election. It is allowed to bypass DF election. And you'll see how this is especially applicable to load balancing modes like single active and to a lesser extent port active also. So the traffic ends up getting rerouted much faster than the DF election procedures, but then rely on the DF election procedures to restore traffic using the what I thought was purple, but the purple traffic path from PE3 to PE2. So traffic does reconverge and takes the load off of the reroute path. Next slide, Stefan, please. So I have here implementation results. So the table in this slide, at the bottom of the slide, highlights the typical results that are seen with an implementation of this draft. So this is showing implementation results from shipping code for some time now. And you can see, actually, there's two things that I want to highlight on this slide is, first of all, by using this reroute, you can achieve sub 50 millisecond traffic restoration. And the other important part that sort of jumps out is the fact that this plays orthogonally to fast recovery procedures, right? So the fast recovery in blue here is not being exercised, but that is the other draft that is in working group last call, and this complements that effectively. And with that, I'm done.
You just have 1 minute left.
For questions or?
Including questions, yeah.
Yeah, so who's the first in the queue? Haibo?
Haibo.
Hello, Luke. Yeah.
Hi.
Can you hear me?
Yes.
Firstly, I agree with your proposal, but I think I find that there was a draft of same scenario before. I think probably we may go further on that scenario. There is a draft named FR label, EVPN FR label. It's always the same scenario with you. Thank you.
Okay, maybe ping me offline and we can discuss, yeah.
Gwen, go ahead.
Hi, Luke. Thank you for the
Hi, Gwen.
presentation.
Sure.
Hi. So I have a questions, a couple comments. One, EVPN FRR for non-unicast traffic, you can done this with, as you mentioned, with a special label. So there's a draft presented a couple IETF ago, but was using a special, not using a special label. With your proposal, the comments is you also need to consider VLAN aware bundle service. And if you have for VLAN aware bundle service, you may have a 4K bridge domain, and also need to consider the label allocation scheme with used. It could be a label assigned per BD. In that case, you may need one label for reroute for each BD. And so it depends, label per BD, label per MAC, or label per VERF, right?
I actually agree with you, Wen. So I left that out. I left that out of the presentation. I do go into it a little bit. So we do address it in the draft to a certain extent, but I left it out of this presentation because effectively all three can be done.
Yes.
So the special label can be per bridge, per AC, or per MAC, and the net effect would actually be the same because it's a local decision at PE2 of what label it's allocated.
That's right. And but you need to consider in that case, once especially label per bridge domain or label per EVI, this has much to do with the forwarding model. Then you need to do you have to support two forwarding model in the local PE. In that case, maybe it will be convenient just to make implementation simpler, has a one forwarding scheme on the egress P. Otherwise, you need to do a different forwarding scheme because of label allocation, different label allocations. And
Okay.
the others, this is the scale concern. Yeah.
Okay, I'm really sorry, but we have to cut
Yeah,
this
I just have
discussion
a
now.
one.
Please take it.
Yeah, one more comment about
No, wait,
submission.
I'm sorry. We are already out of time, unfortunately. If you
Do you
can
want to just
discuss
email me
offline, that
one?
will be better.
Yeah, I'll connect with you offline then.
Yeah, thank you.
Thank you. Okay, next
Thanks,
presenter, Ali.
Can you guys hear me? Hello.
Yep.
Okay, I think we lost Stefan.
He's still there. I think he's still
right.
there.
You can go ahead.
Okay, great. So this is a updated version for the secure EVPN, Rev 05. And next slide. Hello. Okay. So a little bit of about the history of this draft. The latest Rev, the main difference between the Rev 05 and the previous Rev 03 that was presented is the merge of IPsec-ME control IKE draft, which was a companion draft of this draft into here. And the two got merged because of the synergy between them to have one comprehensive draft that covers both the procedure of the rekeying as well as the framework and the architecture for the security VPN and BGP routes that are needed. Next slide. The main changes relative to Rev 03 is basically the addition of section 4 and 5. And section 4 talks about generating the initial IPsec security associations. And section 4.2 gets into the rekeying of these essays. And it covers single IPsec device rekey as well as the multiple rekeying for the multiple devices. Section 5 covers IPsec database generation that includes security policy database and security association database, as well as peer authorization database. So those are, and these sections basically got lifted from the IPsec-ME Carol draft in here. Next. Another change in here was the correction for one of the encapsulation. It covers correction for the diagram. There are two encapsulation. One is VXLAN encap within the ESP, and then one is VXLAN encap within the ESP, which is itself incorporated within the UDP. Figure 5 of the draft, in the previous Rev, it was correct, but there was a cut and paste error, and we corrected that issue in this Rev. Next slide. So basically, this draft has been around for a few years, and it has been stable and baked. And after we were waiting for merging the draft, with the other one, and I think right now that we got it merged and everything is in one place. It is ready for a working group adoption call. All right, that is the end of my presentation.
Okay, we can go to the questions. When?
When you're on mute, you might.
Head start.
Okay, we can. What happened? Okay.
Sue, do you want to go ahead with your question? We are not able to hear you. We can't hear you, Sue.
Ali, thank you for merging the two drafts. I can see that there's quite a lot of text moved in from the draft. I will ask one key question and then follow up with minor points to the list. The main question is, how much dependence does the web of trust in BGP play for the security associations? In other words, how much is that the key requirement for the security, and how much does Section 4 work or work based on that?
So for the BGP sessions, we expect the BGP sessions to be completely secure and either to be done via the TLS or IPsec. So those are the connection between the PEs and RRs. The BGP connection, it is expected to be completely secure.
So
and,
that is
then
that is a base requirement for all the security that follows in the draft. Okay,
yes.
I will send the rest of my comments via list, but I wanted to make sure I understood that. Thank you.
Sounds good. Thank you, Sue.
Thank you. Next speaker, Jorge.
Hello, everyone. So this is domain path for Ethernet VPN interconnect networks draft. Next one, please. So this is the agenda. We can go to the next one. So basically, this draft is about taking the domain path attribute that is defined in the EVPN IPVPN interworking draft and use it also for EVPN layer 2 routes. So a short refresh about the route is basically what you have on the slide. So domain path is an optional transitive attribute. It's composed of a sequence of domain segments where each domain is defined by a length and a sequence of domains. You see here the format of a given domain, including the domain ID and the SAFI type, where the SAFI type can be EVPN, IP, VPN IP, or 0 for local routes. So the whole idea is in the IP, VPN, EVPN interworking draft that each service gateway with an IP verb connecting two domains can actually add or append a new domain for the routes that the gateways are re-advertising to the destination domain. And the DPath has impacts on the control plane loop protection, as well as the best path selection. Next slide, please. So here you have two examples. The use case one is basically you have a bunch of gateways that are interconnecting different domains. So P4 originates a route, and route type 5, it goes to P3. P3 installs that into the IP verb and re-advertises that into a second domain in an IPVPN route. And when it does that, it slaps a DPath with domain 6500:1:EVPN. and so on and so forth for the gateways P2 and EVPN P1. So the idea is if P1 and P4, they have a backdoor connection or a peering, and P1 re-advertises the route back to P4, P4 can actually recognize the one of the local domain IDs as his own local domain, and can actually prevent re-advertising back the route. So basically, it drops the route. A more simpler case is the use case 2, which is a typical data center gateway loop protection, where you have a P1 advertising an EVPN route type 5 to gateways 1 and 2, and they exchange the routes in an IPVPN address family. And because of the the domain path, they can actually identify a potential loop, and they do not re-advertise the route back to the EVPN domain. Next one, please. So what we are doing here in this draft is use the DPath for non-inter-subnet forwarding EVPN routes. In particular, you have here the some details for the MAC IP advertisement routes when those routes are not used for inter-subnet forwarding. And here, basically, we are not connecting like the domains as defined in the EVPN, IPVPN interworking draft, but what we are interconnecting here is layer 2 domains, and the layer 2 EVPN gateways between the domains are actually modifying the DPath. And here we also use the SAFI type is going to be always 70, so EVPN. But other than that, the gateways will use similar procedures. And the use cases are typically the RFC 9014 interconnect gateways. And we can reuse this attribute to detect the loops, in a very simple way. And because of the capabilities of this attribute, we can also use it for route traceability or best path selection. Special attention to section 4.2 in the draft that summarizes the current best path selection for MAC IP routes in general. So it should be looked at with, in a careful manner. Next one, please. Yeah, so I have two examples that we have in the draft here. A very simple one, you have data center gateway 1 and 2. It's for an EVPN RFC 9014 interconnect. So a MAC route makes it to data center 1 and 2, which we advertise that into another domain. And because of this attribute, we can protect the loop. If you go to the next slide, we have another example. Yeah, next one, please.
Isn't it the 7? Which slide do you want? Is it 7?
Yeah, this one. Yeah, sorry.
Okay.
Yeah, it took a while on my screen. Yeah, sorry. Yeah, here is a similar example, but now in data center gateway 2, you have a local attachment circuit and an SE connected to it. So you advertise that MAC route with a special local domain ID, and data center gateway 1, you receive both. If you configure the same domain ID for local routes on both, data center gateway 1 can actually drop those routes immediately. Another way of doing it is even in data center gateway 1 and 2, they do not share the local routes domain ID. You still prevent routes because let's say data center gateway 1, for instance, selects the one coming from domain 1. It'll re-advertise to domain 2, but now appending the new domain ID. So the route that is advertised into domain 2 will have domain ID 1:1 EVPN, comma 1.3:0. And that can be used, first of all, on the peer data center gateway to identify that this is coming from, it's potentially a loop. So it's, data center gateway 2 is not going to re-advertise that into domain 1. And also EVPN P2 can take that into the best path selection and use the one that was previously advertised by Data Center Gateway 2 directly. So basically the forwarding will be properly done. Next slide, please. Yeah, and this is pretty much it. So this is first, version 00. So we are looking for feedback. So any questions or feedback are welcome.
Okay, no question. I think we can move to the next. Ali? Go ahead, Ali, and unmute yourself.
Please hear me? Okay.
Yeah.
Jorge, thanks for the prezo. Quick question. So basically, this is enhancing the procedure in RFC 9104 for the to connect two domains where it is covered over there. In here, we can expand it to beyond two domains to do loop prevention as well as bed path selection.
That is correct. Yeah, it's extending the procedures in 9014. Yeah.
Okay, very good. Thanks.
Thank you.
Okay, so Jorge, you are also the next speaker. Let me change the slides about IP aliasing.
Yeah, okay. So yeah, this is the version 03. So can you go to the next slide, please? Yeah, so in revision 02 was presented in the last IETF, and we were talking about 3 different use cases for IP aliasing. So one was for Ethernet segments for host routes in symmetric IRB, second use case for interface-less and host routes, and the third use case is for IP prefix routes when the Ethernet segment is a layer 3 construct. So in version 3, basically we added an example for use case 2. There was some feedback on the main list that triggered some clarifications as well. In particular about the Ethernet segment when it's used as a layer 3 construct, which is a new concept. And we also added section 8, which talks about the compatibility of IP aliasing and the unequaled ACMP draft. Next slide, please. So yeah, one of the points is the how you construct this layer 3 Ethernet segment. And the idea was that for this use case 3, basically the Ethernet segment is really defined as a set of layer 3 links that are connecting the multi-home leaves into the same CE. The ESI in this case should be a type 4 using the router ID of the multi-home CE for the ESI. We can also run DF election if we have single active. There is no need for it in null active, but in single active, yeah, it's an option here. And then with that, all the PEC routes that we receive on the CEs with the loopback as the next hop. I mean, the loopback that is defined for this Ethernet segment, if it is received as a next hop, the re-advertised routes type 5 will use the associated Ethernet segment identifier. Next slide, please. So yeah, so the draft is it's been around for quite a bit, and I think we addressed all the different comments and and feedback. So we believe the yeah, it's definitely ready for a working group adoption.
Any question? Okay, if no question, we will move to the next speaker, Jeffrey.
I'd like to share the screen myself because I have some animations to help
Sure.
things understand.
Sure. Let me stop sharing. Go ahead.
So what oops, I'm sorry, hold on a second. I think I'm going to I'm going to have to ask a chair to share. I'm sorry.
Okay.
I have some settings not fixed. I tried it earlier, right? Okay. MVP and regional segmentation. Next slide, please. So let me start with the background. We have RFC 7524, which is about MVP and VPOS inter-area segmentation. Basically, a provider tunnel from PE to PE consists of inter-area segments of different types or instances. For example, you can have MLDP tunnel in area 1, but RCP P2P tunnel in area 2. But the way it works is that area border routers, they work as route reflectors. They modify the tunnel type and identification in the PIN-Z tunnel attributes that is attached to the PIN-Z AD routes when they re-advertise the routes to the next area. They also update the community. It is called segmented next hop extended community. It's basically another protocol next hop embedded in the message in the BGP update, so that's when the PEs send back, when they need to send back leaf AD routes, they will send back to the router identified in this community. Now that is limited to the inter-area case and also limited to LSPs. Both these limitations can be removed, and this is what this draft is about. Next slide, please. So to remove this area limitation, we introduced this concept region. So even if you have a provider network is a single area flat topology, you can still define regions. Actually, before we get to the regions, we can first talk about how, even in the inter-area case, how it can be done for inter-area. To modify that PIN-Z tunnel attribute and that extended community, typically we have a BGP neighbor group, so that all peers in that same group will get the same PTA and that's segmented next hop extended community. Because of this BGP neighbor group, we can allow the segmentation at the regional border routers. A region can be arbitrarily defined because of that BGP neighbor group. It could be an IGP sub area, or it could be an entire AS plus some external links, or it can even span multiple ASs. So to do the inter-region segmentation and instead of inter-area, we actually don't need a new signaling. And this concept is already adopted in the EVPN bound procedure updates spec. Next slide, please. So that's the inter-region segmentation. Now, the next one is we can actually extend it to intra-region so that we can do assisted replication. Here is an example. Too bad I cannot use animation here. But we have 3 areas, those three blue clouds there. The first area or first region is enlarged to show where the focus is. We have PE1 as the source PE, and we have a few other PEs in the same region. And then we have some others in the other regions on the right side. What happens is that when the PE1 advertises a PIN-Z route, it gets re-advertised by the first border router there. When for inter-region, when the border route re-advertises, it updates the tunnel attributes. But when it re-advertises into the same region, those are not modified. Now, in case in ingress replication, what happens is that all the PEs in the same region will send back a leaf AD route directly to the source PE, and then the source PE tracks those leaves, and then we'll do ingress replication to all of them. Now, if we extend the inter-region segmentation to intra-region as well, basically when the first ABR or RBR are re-advertised back into the same region, it also modifies the tunnel attributes. Then you get intra-region segmentation, and which achieves assisted replication. Next slide, please. So this is this shows that when the SP1, which is stands for a segmentation point, as it is the regional border router there, it re-advertises with a modified tunnel attribute and extended community. That way, the source PEs, the PEs in the first region will send a leaf AD route back to SP1 instead of PE1. And because of that, now the PE1 will only send traffic to SP1, who will then relay the traffic to both PEs in the same source region and in the next region. Next slide, please. Another issue here is the bot node support. So here the segmentation point stitches the upstream segment to downstream segments. This is done by label swapping. But it could also have local receivers, and that needs to do IP forwarding. The implementation typically can replicate the incoming packets for both label swapping to downstream segments and for IP forwarding local VRFs. But sometimes a particular implementation may not be able to do that. It's just because of limitation of the device. So it needs one extra copy. So one copy for label swapping, another copy for IP forwarding. Next slide, please. So this is about optional procedure for a bot node to request an extra copy for local IP forwarding in the context of the segmentation. It's optional. It's only accommodate certain bot nodes with a limitation. Now, if the upstream tunnel segment is RCP P2NP, then the RCP P2NP signaling can actually request the upstream PHOP nodes, which could be which is a P router, to send the extra copy. Nothing else needs to be done. But if the upstream tunnel is ingress replication or beer or MLDP, then that extra copy needs to be tunneled directly from upstream PE or RBR. It cannot be done by a core router. So this request is sent by tunnel encapsulation attributes in the leaf-AD routes. I'll leave the details to the draft. Next slide, please. So summary is that the inter-area segmentation extended to both inter-region and intra-region. This does not require a new signaling. It's just that for intra-region case, the area border router needs to update tunnel attributes and extended community, next hop extended community for inter-region purpose. And then it allows the bundle to request an extra copy for local forwarding. This is a zero version of the draft. I appreciate comments. That's my presentation for this one.
Ali, go ahead with your questions, but really quick.
Sure. Jeffrey, thanks for the prezo. Quick question. In your presentation, you didn't cover the redundancy when we got multiple gateways for the intra region. Is your draft covers, the redundancy and the DF election aspects of it?
The redundancy is already covered even by the original RFC 7524. It's because the leaf-AD routes, the egress PE will only pick one segmentation point as the upstream, and send the leaf-AD route towards that one. So you will not get duplicate traffic.
So you might want to put a short note or a short section in this draft.
Sure.
All right.
Thank you.
Thanks.
Okay. So you can go ahead, Jeffrey, with your next presentation.
Okay, thanks. So this draft is about controller using MVP and EVPN for provider tunnel discovery. Presenting on behalf of my co-authors, Rishab, Sandy, and Human. This is actually a draft that is 2 years old. We published draft, but actually didn't present it for a while. And I think it's time to try to move this forward. Next slide, please. So let me first summarize the potential usage of a controller in an MVP and EVP network. The first one is that is the calculation and the signaling of the provider tunnels. This is covered by two drafts. The first draft is basically how to set up P2P, SR P2P tunnels in the underlay. And the second draft is the MVPN, EVPN, SR P2P, which talks about that ingress PE collects the tree information, the provider tunnel information, and which includes the route information, leaves, and constraints, and then pass on to controllers for calculation and signaling. The next usage of the controller is that the controller can actually directly set up overlay forwarding state on PEs, which can completely remove the need for MVPN signaling protocol. Presumably, the similar could be done for EVPN and BOM traffic, but I had not talked about it in that draft yet. So that is covered as in the BGP multicast controller draft, which covers other things as well. And finally, the controller could actually participate in the MVP and EVP signaling to collect signal provider tunnel information at the overlay. That way, we do not need the ingress PE to first collect the tree information, which include leaf information, and then pass on to the controller. The controller will just do its collect the information itself, and that is what this presentation is about. Next slide, please. Some quick background for the tree and leaf discovery. This term PMZ, Provider Multicast Service Interface, is always a tricky term, but it's basically a logical interface used by PE to send overlay data to some or all the PEs. You could have inclusive PNZ or selective PNZ, and we have corresponding AD routes that announces tunnel that used to instantiate that PNZ. We talk about that ingress PE advertise IPNZ AD routes, and then they may track leaves explicitly. And based on the tracked leaves, the ingress PE will trigger tunnel setup. In the old days, if you're using RCPT P2MP tunnel, the ingress PE will ask the RCP module to set up the tunnel. In the controller case, the ingress PE pass the tree information to the controller to calculate and set up that SR P2MP tree. Next slide, please. Now, the basic idea of the main topics for this draft is that the controller will do the tree and leaf discovery by participating in the MVPN, EVPN signaling to collect the tree information. Here, if you look at the picture on the right side, I have numbered those routes. Basically indicate the sequence of the events or which corresponds to the animation. Now, the first step is I'm using the SPNZ example. PE1 advertise SPNZ routes. The controller is participating in the signaling. So the controller gets that SPNZ route. It knows that, oh, okay, for this SPNZ, I'm using this provider tunnel with the root ID and tree ID that the ingress PE gives. And then it re-advertises to other PEs in step 2. Now, PE2 and PE3 gets that SPNZ route, send the leaf AD route back, targeted at the controller. So now the controller knows that the PE2 and PE3 are the leaves. So it has the entire information, the tree ID, the leaf sets, so they can set up the tree using the controller to tree node signaling. Now, for the egress PE to direct the leaf AD route to the controller, then the ingress PE will attach an extended community to the PNZ route that basically encodes the controller's address. So now the tunnel leaves will use that information to construct a route targets attached to the leaf AD route so that it can be targeted at the controller. That's the basic idea. Next slide, please. Now, in the previous example, the ingress PE originated the initial PNZ route. Now, for ingress PE to advertise the PNZ routes, it typically is done because of the configuration. And that configuration is from a central planning entity anyway, ahead of time. So what if we relieve the ingress PEs from that burden of learning that configuration and advertising those PNZ routes? We have the controller that is pre-loaded with all the information that is planned by the central planning entity. And then it will just advertise the PNZ routes on the ingress PE's behalf. So now you can see that in the first step, the controller advertises the PNZ routes, and then at the PEs, they will send back the leaf AD routes if they determine that they are the tunnel leaves. So this not only relieves the ingress PE the burdens of learning the configuration and advertising those routes, it also makes the DCB label allocation easier. The DCB label is it's basically like a global labels or similar to the sRGB labels. Basically, all the PEs will use the same label value for VPN or for Ethernet segment. So they must be allocated from the common block by a central entity. So that could be the controller itself. So now the controller has all the information and to advertise the PNZ routes, and then with the DCB label allocated from that block. There are some special considerations when the tunnel segmentation is used. Next slide, please. So in previous case, we talked about controller advertising those PNZ routes. Now, in a segmentation case, because we want the propagation of the PNZ routes to follow a certain order to go through all the segmentation points. So if we don't do anything special, those routes may be propagated out of order, and then we don't get the benefit of segmentation points updating those attributes we talked about in the previous presentation. So in this case, we need a controller to target the ingress PEs first, even though when it is advertising routes on behalf of the ingress PE. So the first step, the controller advertises PNZ route towards PE1, and then PE1 and then gets it and then turn back and advertise to everyone. Now this extra step is achieved by manipulating the route targets. I think I'm going to skip some details here. And next slide, please.
Yeah, you have to conclude, Jeffrey. We are already behind the schedule.
Yeah, okay, yeah. Can we get the next slide? Yeah, summary, yes. So we talked about the controller advertising the participating in signaling, including controller learning the tunnel ID and leaf information, and advertising the PNZ routes on behalf of PEs, and then that allows the DCB label allocation more easily. And so that's the idea. Comments appreciated.
Yeah, Ali, I'm sorry, but we don't have any time for questions. So please make it to the right.
All right.
Thank you.
Next speaker, Yao.
Hi everyone, I'm Yao from CT, and this draft is about the issues that may be encountered during the deployment of SRv6-based BGP services in the SRv6 and MPLS coexistence scenario, and the possible solutions. Next slide, please. The best SRv6 services draft defines how BGP messages between PEs may carry SRv6 services to form VPNs. It relevages the existing AV surface of MPLS-based VPN routes. The SRv6 service set is a set associated with a service-specific endpoint behavior on PE. This set or part of the set is enclosed in SRv6 service tier V within the BGP prefix set attribute, which is attached to existing MP BGP NLRIs. And there are two methods to encode SRv6 service sets. The first method, the SRv6 services are encoded as a whole in the SRv6 service tier Vs, and the MPLS label field of the corresponding NLRIs is set to implicit none. The second method, the SRv6 service tier V, carries only the locator part of the set and the function and argument part are encoded in the MPLS label field of the NLI. Next slide, please. And this figure shows the coexistence scenario. P1 is a legacy device that only supports MPLS VPN. On P3, an SRv6 service set and an MPLS VPN label are assigned for the same service, service 1. And both the SRv6 VPN route and MPLS VPN route of P3 are sent to P1. And since P1 only supports MPLS VPN, it may discard the SRv6 service TLV and treat the SRv6 VPN route as an MPLS VPN route for service 1. Then there are two MPLS VPN routes for the same service 1 on P1. And then on the data plane, P1 may choose the wrong route, which is originally the SRv6 based route, and use the label field in the NLI of the SRv6 VPN route as the MPLS VPN label for packet encapsulation. And after P3 receives the packets, it may send the packet to the wrong service instance or drop the packets. We can see from the example that legacy devices may wrongly treat the SRv6 VPN routes as an MPLS VPN route, which may result in service failure or abnormal extra traffic flows in the network. Next slide, please. To avoid this problem, the SRv6 services draft suggests that implementations should provide a mechanism to control advertisement of SRv6-based BGP service routes on a per neighbor and a per service basis. One common way to do this is by configuration. And first, the network operator should obtain whether the PEs are capable of SRv6-based service routes. Then the operator configures some PE or route reflectors based on each PE's capability. The per neighbor configuration specifies which PEs can the SRv6 service routes be sent to. This method has some disadvantages, especially in the large-scale networks. The per neighbor configuration needs to change with device capability, and the additional steps of getting the capability of PEs and the configuration increase the possibility of faults and the difficulty of troubleshooting. And since there's no standard solution for the network operator to obtain the PE's capability for SRv6-based service routes, there may be interconnection problems in a network consist of devices from multiple vendors. Next slide, please. And to control the advertisement of SRv6 service routes without per neighbor configuration, this document uses a simple way. It defines a new capability code for SRv6 BGP service. And a BGP speaker must not send any update message that includes the SRv6 service TLVs on a particular BGP session unless it has sent or received the SRv6-based BGP service capability in the open message on that session. And like other BGP capabilities, if the capability for SRv6-based service routes is enabled or removed on the device, an established session needs to be reset to resend the open message. And in this way, it is easier to implement and manage SRv6-based services in the network. And next slide, please. Yeah, that's all for the draft. Thank you.
Question? Okay, thank you. Let's move to the next speaker. Pascal.
Stefan. Can you hear me okay?
Yeah. You can go ahead.
You can go ahead. Good. Can you, next slide, please? So this is a new draft which basically discusses the quality of the information that's being redistributed in EVPN, and in particular, we are trying to alert the community that with IPv6 Slack and the way we are snooping it today in our networks, we are probably, as we say, we are probably building on sand, meaning that we are building a very solid architecture on something which is not solid at all. If you think about DHCP-v4, IPv4 in general, we can build something solid because DHCP is stateful, and we can observe the DHCP exchange, make sure that it happened in both directions, and so we can reasonably well snoop the DHCP and derive a state of which IP address is where with which MAC address, and then inject that in VPN or anywhere else. With DHCP-v6, arguably we can get same result and have a reliable state that we can inject in the fabric. Now, IPv6 comes in with stateless address configuration, which is a major way of forming addresses. And as opposed to the DHCP Slack stateless address configuration is not stateful. It's not deterministic. You don't know when the nodes will form addresses. You don't know how many addresses they will form. You have no idea when the nodes release those addresses. So you end up with a state which is only partially valid with regard to what the host really wants and do. For instance, there is this case that we call a silent node where we have missed or forgotten a broadcast, like a duplicate address detection, that message by the host, and we have not learned that the host has this address, so we have forgotten it. And there's no way it's going to be reformed, and now we stay with a missing guy. And because it's missing, if somebody looks him up, this has to be a broadcast, the U in them across the fabric, which is really something we don't want to have. Similarly, when the node ceases to use an address, and that can be very often, the nodes can really form maybe say an address per day and release one address per day and maintain like 7 addresses. That's quite typical. We might very well maintain addresses and state in our networks for addresses which don't exist. So we are wasting resources as much for state as for bandwidth in the case of silent nodes. And there is no information in Slack about when the device moves and what's the order of movement, etc. So even the location, the latest location of a given IP address is uncertain. And that's just for maintaining the addresses, but the fact that Slack relies on broadcast is also opening not only to too many broadcasts in our fabrics, but also different sorts of attacks which can be very harmful, like DDoS attack against addresses which don't exist and for which we have to broadcast. Another angle, which is more like for IoT, is the way Slack is built imposes that the devices defend their address. Like they can respond to NAT, they can respond to NS, and if they don't, then an attacker can actually take over the address. But even if they do, sometimes the attacker can take over the address. So the end result is when you want to deploy a solid VPN network based on this kind of unreliable, undeterministic information about the address, is you're bound to face problems in the field. In a lab, it will work fine. And then someday in the field, you will have those very hard to debunk situations, which are really due to the fact that you don't have a real stateful information about the address. And it's MAC appearing. Next slide, please. Stephen? Yeah. So this is just a reminder of what I just said. Slack is prone to attacks. We can have bump flows just because of silent nodes, which can exist, and they do. Snooping only observes a portion of the messages, has no concept of order. So we don't know for sure where the last location of this address is, and if it's still in use at all. Next slide. Now the IETF has come up it started in 6LoWPAN working for IoT because really IoT cannot have broadcast just the way even fabrics can. So there was no way to accept all those broadcasts, and the IoT finally, after trying, went for a stateful approach for auto configuration, and that's RFC 8505, which defines a mechanism whereby the host talks to the router and agrees with the router that it's going to have this address and this address MAC mapping, and there will be a lifetime, there will be a unique ID associated to this, meaning that with the other RFC that you see here, 8928, we can actually check when the address shows up somewhere else in the network that it is the actual user owner of the address. So all of a sudden, if you start deploying 8505 and 8928, there cannot be an address in your tables that is not effectively in use. You're not missing any address because you have an effective state for each of them. And an address cannot be stolen. And because you know every damn address in your network, if there is a DDoS attack against address which don't exist, a scanning DDoS, well, that one will just fall into the null zero, basically. So this brings two things: a stateful, reliable state for each and every address, and a secure, that's why you find secured in the title of this draft, a secure knowledge that the guy for whom we inject an address in EVPN is actually the owner of this address. And we can do savvy, we can filter traffic that comes from a guy who is impersonating somebody else, because we know for sure where the owner of this address is. Next slide.
You have less than 4 minutes left.
That's okay, I don't have many slides. So basically, this is a summary of what I just said. This is how the interaction happens. Starting from bottom right, the node auto-configure whichever IPv6 address it wants. But instead of doing that, waiting 1 second, etc., involving a broadcast, it just tells the router, Mr. Router, please, can I have this address? The router checks, step 3, based on policy, blah, if this guy can have this address, it goes through the distributed database, which is EVPN, whether this address already exists. And because we have parameters, we know if this address already exists, if it's the same owner and it has moved, if this is the most recent position, or if it's a different owner, in which case it's duplicate and we have to reject. So we have all this information available without doing anything on the network. Next slide, please. So this is more detail than the previous slide about how stateful address configuration works. But basically, there is always an abstract registrar, a whiteboard, where we list every address, every mapping. And as it goes, EVPN is a perfect example of how it can be operated as a distributed database. Next slide. You could think less as the centralized variation of that. So this draft is about redistributing 8505 and 8928 into EVPN. We can do we basically, as I said, distribute the registrar, which is called 6LBR, and it is now in every PE next to the BGP table. We have this UNI direct interaction with the host, and we have to modify the MAC mobility extended community, and we provide backward compatibility with the existing operation. And with the modified MAC mobility extended community, we provide this rover, this proof of ownership, it's actually the hash of it, and the TID, which is the sequence counter. And based on those two information, we can effectively discover if when the guy shows up somewhere else, it's the same with a fresher sequence, or if it's a different, in which case we can say duplicate without going through the exchanges that exist today. And I think I'm done. But next slide. I think that's it. Yes, that's it. So ready for questions.
Jorge, go ahead.
Yeah, Pascal, thank you for this. You are actually extending the MAC mobility extended community. However, RFC 9047 defines a new extended community that is especially for ARP and naval discovery protocol things. And so I wonder why you didn't use that one instead of the MAC mobility extended community. Seems more appropriate.
Oh, can you please put that on the mailing list or send me an email and we'll examine that? I mean, let's look at it. I don't have an answer. It's just because we didn't look, right? Probably.
Okay, sure. I will do that. Thank you.
If you could, it would be very, very neat if you could look at what we have today in this new extended community and propose a way to use the other one and how we would structure it. That would be really appreciated.
Okay, thanks.
And think about the backward compatibility. One key aspect here is once we supported 505 and we face someone who does not, we need to sort out who's the winner. And normally we say the guys who supported 505, since they can prove their stuff, they are the winners. And so we played with the writing of the sequence in such a way that the 9505 derived sequence is always a higher number than. So that's why it's on the left. You'll see that. So please consider that when you do your proposal.
Sure. Both extended communities are actually compatible. You can use them in the draw type 2 with no issue.
So we basically added a few flags just to notify, for instance, that we do effectively check, for instance, the source address validation, right, with this rover thing, which is the ownership token. That is actually, the rover is actually a rover and stuff like that. So we have those like 4 or 5 sticky bits. So if you can look at all that, I mean, let's have emails. But yes, that would be nice. Thanks so much.
Thank you.
Thank you, Pascal. Next speaker, Aibo.
This is Haibo from Huawei. Can you show the slides? Okay, yeah. This is our new draft about the advertising SBFD discriminators in BGP. Next, please. I don't see the show the next page.
I moved to.
Okay, perhaps there may be some problem with my network.
Do you want to?
Okay.
Do you want to share on your side?
Okay. I can use my slide to see. You may share. Continue. Yeah, for the page 2, our motivation is that the RFC 7880 defines the SBFD mechanism. We may use the SBFD to detect the PE failures quickly. For deployment for SBFD for IPv4 network, the reflector, we may use the SID address as a discriminator. So we can simplify operators configuration. But for IPv6 network, the discriminator for each destination PE we must configure manually. There are also two RFC 7883 and 7884 define the is and the OTPF extension to flood the SBFD discriminator, but they can only use in inter-domain and may create unnecessary SBFD sessions. Page 3, please. Here is the first scenario, the service for the service over SRv6 PE. There are two AS, there is that inter-domain scenario, and also it may be also used for inter-domain. P1 and P2 advertise their VPN routes, which contain the SRv6 VPN seed to P3. The traffic arriving at P3 will be forwarded to P1 or P2 based on SRv6 locator reachability. P3 needs to create the SBF session to detect P1 and P2's locator reachability. For each SBFD session, we must set the remote IP address and the discriminator manually. When the PE when there is a large number of PEs, the configuration will be more complex. Also, IGP may flooding the SBID discriminator, but they count across the AS boundary. Even within one AS in intra-domain, the nodes may be create a redundant SBID session because IGP flooding will flood into every node. Page 4, please. For Sentinel 2, there is a service over SRv6 policy. In this Sentinel is similar to the Sentinel 1. And also it can be used for intra-domain. The VPN roles also advertise from P1 and P2 to P3. But they are in this Sentinel, they will use their IPv6 loopback address as a net hop. The traffic arriving at P3 will be forwarded based on the SRv6 policy reachability. And P3 may be create a SBID session to detect the P1 or P2 reachability. For each session, there we may use the remote IP address definition to P1 and P2 the loopback address, and configure also manually configure the discriminator for the SBID session. In practice, this Sentinel is not limited to SRv6 policies, and they also may be applied to MPLS Sentinel. Page 5, please. This is our extension. We may use the BP extension. We may reuse the BFD discriminator attribute, which is defined in the for the IFC 9026, and it has defined as the type 38. We introduced two new BFD modes. The type 1 is SBFD for SRv6 locator session. This is only used to detect SRv6 locators. And in this mode, we may use the optional TLV will container as a source IP address TLV, which contains the SRv6 locator address. And also we may introduce another type 2, another type for BFD mode, means the SBFD for common session. In this type mode, we may use the user to detect roles net hop. This mode can be used for both IPv4 and IPv6. The optional TLV will contain a source IP address TLV, which contains the net hop address. Page 6, please. This is the procedures. First, for the advertising BGP speaker, the VPN roles may advertise with a local discriminator carried in the BFD discriminator attribute. Then the BFD mode is set to one of the new modes defined. For the receiving BGP speaker, we may use the discriminator to notify the BFD model to create a SBFD session. For mode type, for model 1, the locator carried in the source IP address TLV is used as the destination of the SBFD session. For the model 2, the next hop address carried in the source IP address is used as the destination. Page 7, please. First, I may thanks Greg's comments. He gave some more, much comments before this meeting, and also we welcome more comments and discussions, and we may revise the draft accordingly. That's all. Thank you.
Greg?
Greg?
If we can go back to the previous slide. My question, and I tried to express it in the comments before the meeting, was it's not clear how BFD control messages are encapsulated. So are they encapsulated with the same as a traffic with the service 6 policy or something else? So the receiving speaker, what the network layer is used to transmit SBFD packets.
Okay. Okay, because I have received much comments from you. Yeah, I see that we may describe the not very clear, and for this scenario, we may describe it more clearly after this meeting, and we may update our drafts. Okay.
Yeah. Yes, because
thank you.
BFD is not really able to differentiate between the path failure and the node failure of end node. So I think that that's something to be aware of and understand of what is possible to track and what you are really monitoring. Another note I want to add is that because of EVPN, you might find that you're duplicating, you have twice as many SBFD sessions as you would have if you use a BFD. Because if each of the PEs involved advertise its own discriminator, then other PEs will start SBFD sessions. So you are multiplying by 2 the number of BFD packets being in the network. Okay, something to think about. Thank you.
Okay, thank you for your comments.
Yeah. I just had thanks. I just had a sort of generic comment really about where this lives, because it wasn't clear to me looking at the draft if the primary objective is simply advertising or flooding the reflector discriminator in BGP, or if it's also defining these new session types for particular services. If it's simply the primary function is just to have a mechanism in BGP to flood the reflector discriminator, similar to what we have in the IGPs, I'm not sure it really lives in BES, that part of it. Secondly, if you're defining your SBFD session types for particular services, we also probably need to talk to the BFD working group. That was it.
Okay.
Jeffrey?
Okay, thank you for your comments. Yeah, because this draft.
Hi. Sorry, microphone issues. Jeff Haas is BFD chair. I think the reason why answering Matthew's comment, this had originally gotten broached as part of a BFD attribute that originally was done as part of best work, which I suspect is why it is being brought to your original attention. We'll be taking a look at this draft, and if it needs to move over to BFD, that will be fine. But we'll have to take a look what the scope of it actually is.
Okay, thanks.
Okay, thank you for your
thank you,
comments.
Aibo.
Yeah, that's true. Yeah.
Okay, next and last speaker, Yubao. Not this one. Yubao? Okay, we don't have our last speaker on the attendee list.
They're on the
yeah,
meet-
it's there.
Yeah.
You bow? I just sent a message to him.
Okay.
You bow? Do you hear us?
He's answering in the chat, Stefan.
Yeah, I sent him a message, but I'm not getting any reply.
Can you
Okay.
remotely unmute him?
No, I don't think so.
Okay.
I don't think we have an option to do that.
It's just in case he's on mute.
Yeah, he says he has a problem on the chat, but not sure what the problem is.
No, we can't hear you. Hello? Hello?
Hi, can
Hey,
you hear me?
yeah, yeah, yeah.
Sorry. My
So,
audio
so
is not.
go ahead, but you will. I don't think you will be able to get your 10 minutes because we will be cut at some time. So
好
please start now. Okay.
好，based on FC, my subject is our sub-distributed bumper in the world use case. Next page, please. Based on FC9136 bumper in the world use case, centralized forwarding is adopted for inter-subnet communication. That means all inter-subnet flow must be proceeded by DC gateways. This will burden the DGWs. In order to decrease DGW pressure, distributed forwarding should be considered for inter-subnet communication, especially when AVEs have the capability of IPv4 forwarding. Next page, please. Thank you. For example, distributed communication between SN2 and SN1 and distributed communication between SN2 and H3 are expected. However, NVE2A and NVE2B only have microwave according to FC9136, so they have no IP routing tables. Thus, direct inter-subnet cannot be supported. Next page, please. We can configure an IPv4 instance to each NVE in order to activate their inter-subnet forwarding capabilities. On this basis, we can go a step further to achieve the distributed inter-subnet forwarding behavior. In this case, the advertisement of the RT1 per EVI routes of ESI 23 should be changed from FC9136 because AV8 don't have an instance of BD10. As illustrated in this figure, when AV2 advertise RT1 at AV2 at 10 for BD10, and when AV3 advertise RT1 at AV3 at 10 for BD10, these RT1 routes are both advertised along with an extra route target. The extra route target is the export route target of a supplementary BD. HAVE and HDGW should be configured with that SBD instance. As a result of that extra route target, these two RT1 routes will be imported into the SBD by AVE8 and the DC gateways. Then the corresponding data packets can be sent from AVE8's SBD to AVE3's BD10 without passing through AVE3's IPv4 instance. Next page, please. As illustrated in this figure, multiple centralized bumper in the world instances are integrated into the same IPv4. When DGW1 receives a RT5 route from one instance, its ESI can't be resolved in the context of another bumper in the world instance. Take the RT5 route RT5 at SN1. For example, when it is received by DGW1 before its ESI is resolved, DGW1 should know that its ESI must be resolved in the context of BD10. Thus, the export route target of BD10 should be carried along with RT5 at SN1. By doing so, when DGW1 receives RT5 at SN1, DGW1 can directly determine that RB1 is its L3 out interface. Next page, please. Thank you. In such case, the RT1 per EV routes RT1 at NVE2 at 10 and RT1 at NVE3 RT1 at NVE2 at 20 and RT1 at NVE3 at 10 will both be advertised for the same ESI, and their Ethernet tag IDs may both be 0 in case of VLAN-based service interface. Thus, when they are both imported into the same SBD by NV8, they can't be distinguished from each other. In order to solve this problem, their Ethernet tag ID should be set to the ACID of their corresponding attachment circuit respectively. But in order not to interfere the MAC forwarding of BD10, we should rely on advertising two different RT1 routes for the same AC1. The first one is advertised in BD10 for MAC forwarding. The second one is advertised in the SBD for IP forwarding. Only the second one's Ethernet tag ID should be set to.
Could you conclude? Could you conclude because we are out of time? So please just wrap up in very few seconds.
Yes. I'm concluding. The second one is advertised in the SBD for IPv4 forwarding. Only the second one, the Ethernet tag ID, should be set to the ACID of that AC1. But their EVP labels should both be set to the EVP label for BD10. And these RT5 routes should be advertised along with a new BGP external community named Sublimiter Overlay Index. Because that the SOI and ESI of RT5 route should both be used to do route resolution in the context of the SBD. Such RT5 routes. Next page, please.
This is the last one.
Yes. Take the RT5 route, for example, RT5 at S1, for example, its L3 out interface is an RB interface, so its ESI must be resolved in the routing table of the broadcast domain behind that RB interface. Then, as illustrated in the tables on the left side, we can use the ESI and SOI of the RT5 at SN1 to do recursive route resolution in the SBD's routing table. After the recursive route resolution, two RT1 per EV routes will be selected as RT5 at SN1's matches. The first match is shown as RT1S at NVE2 at 10. The second match is shown as RT1S at NVE3 at 10. The Ethernet tag ID of them are both the same as the SOI of RT5 SN1.
That's all.
Thank you.
We're out of time now.
Thank
you.
Yeah, sorry.
Thank you.
So yeah, thank you all for your attendance, and yeah, let's talk at the next IETF, hoping it could be a physical meeting.
Thanks
Thank
everyone.
you guys.
Thank you.
Bye.